So our last speaker is Andrei Ivanov, a PhD student from ETH Zürich, and he will present RIVETS that Luca Beni talked us about yesterday. So we are all looking forward to hearing it.
Hello, my name is Andrei, and I am a PhD student from SPCL, Scalable Parallel Computing Club at ETH Zürich, and this work is a part of EU pilot project. So let's look at the problem that we have. If you look at the existing deep learning library specifically optimized for RISC-V, then you will see quite small set of them with most of these libraries focused on inference. For example, the precision only integer or subtype quantized integer, and the libraries that have floating point optimized implementations usually very limited in the amount of kernels that they support. So that's why we want to fill this gap and provide a library for performant floating point training on RISC-V. So for this, we look at the existing deep learning API specifications to understand what actually has to be implemented. There is cuDNN, there is OneDNN from Intel, and there is Onyx that supports quite a lot of architecture. Unfortunately, RISC-V support in them is quite limited or non-existent. So in general, the common thing that they have is the kernels, convolution, matrix multiplication, pooling, statistical normalization, and activation functions. So this is the set of kernels we aim to support. So as yesterday Luca Benini mentioned about this talk, we focus on the exactly hardware he proposes. This is a Snitch cluster, single cluster in the multi-cluster Akami work, and it has 8 compute cores and 1 data movement core. In addition, it has 128 kilobyte fast tightly coupled data memory, which is very fast to access. The data movement core has asynchronous copies. It's special extension provided by Snitch, and compute cores have small float extension to support half precision, quarter precision, and stream semantic registers, and FREP. So these last 2 extensions I will explain here in more detail. So SSR extension is motivated by the desire to remove explicit loads and stores from instruction flow. So let's say you have this assembly. You want to remove these loads by using stream accesses. And how this works, each SSR register now is mapped to standard registers FT0, FT1, FT2, and now they behave as streamers, not as normal registers. So let's say, for example, we have this 3-dimensional configuration with specific sizes and strides, and what it means. We removed these loads, but now FT0 behaves in a strange way, and first 3 accesses go into memory according to the pattern defined by first dimension, then the second dimension come into play, and then the third, and this way you can encode multidimensional access patterns without explicit loads. So now let's look at the second extension, FREP. So how it works. Let's say you have a loop with additions and branches, and you want to avoid them. What you can do, you can unroll the loop if you know how much you want to unroll. However, the best implementation probably is to have a hardware loop that says repeat the following instructions n times, and this resolves the trade-off between unrolled code size and having the branching and increment instructions in the instruction sequence. So with these extensions figured out, let's look at the example of one kernel. Matrix multiplication is probably very annoying now. That's why we pick a less popular one, which is still quite important for large language models. So this is layer norm. Gamma and beta are learnable parameters. Mu and sigma are mean and standard deviation of source array. B is a batch dimension, and n is the number of elements per batch. So because of the limited size of this fast memory, we have to accommodate real-sized workloads by splitting the input into multiple tiles. Then the computation would work in the following way. Let's say you tile across the batch dimension, and then in the fast TCDM memory, you perform two parallel operations. First, in compute buffer, the compute cores perform actual microkernel computation, and copy buffer is used to, in parallel, run asynchronous copies. So if everything goes well, then this is the timeline of execution you're supposed to see. In theory, compute should be perfectly overlapped with copies in and out of copy buffer. So now let's look at the code example, how this microkernel for single tile is implemented. It grouped into 4 stages. First stage is for computing the mean value. Then second stage is to find the difference in denominator. Third, to compute the inverse square root of denominator. And finally, compute the result. So how this SSR extension can be used now, let's say, yeah, it's a bit offset, but let's say we see the source array need to be mapped to this SSR register that has batch and feature dimension n in this specific way. So the shapes and strides configured in that approach. Then, okay, this is again offsetted, and it's supposed to point to the source array again. Here, the source is red, and you see you add third dimension to repeat the 2 slices of completely the same source successes. Then, so this is supposed to point to DST accesses. It adds 4th dimension to perform them, and this behaves like an additional slice in the array of source and destination matrices. So in the similar way, gamma and beta are supposed to be accessed, and then writes to destination. Yes, sorry for this mistake with misaligned highlighting. So next, what is done, H loop is replaced by this frep extension, and in theory now microkernel is supposed to have no branching, no other instructions apart from computation. And if you look at the execution timeline, then you will see that first it starts with barrier synchronization to make sure that all cores see the same up-to-date inputs. Then compute cores proceed with configuring stream semantic registers, while data movement core is performing copies out and in to the fast TCDM. First iteration may be a bit longer because of cold instruction cache, which should be not that noticeable if you have larger workload where copies are mostly covered by compute and only noticeable at the start and at the end of execution. So we evaluated the performance of our implementation, and this is what we observed. We show here the achieved performance and the peak performance, that is a rough estimate of the hardware capability. So how we estimated this? We looked at the number of particular operations each kernel that we measure is supposed to use. For example, absolute value computation requires n element-wise instructions to use this comp unit, then the batched general matrix multiplications requires this number of FMAs, and for layer norm, expression is a bit more difficult, and this allows to look at the peak operations per cycle that are provided by each functional block present on this hardware and evaluate what could be the peak if there is nothing else apart from useful compute operations. Of course, in reality, it's not possible to achieve. So with this, how we see the potential for moving forward, let's say you have PyTorch model encoded in some file, completely platform agnostic, and it has, let's say, for BERT or YOLO v5 models, then we supposed to feed this model into the DSML frontend. So what is it? ML means machine learning, and this frontend is for DACE. DACE is special data-centric parallel programming framework, which can perform compiler level optimizations, but it's actually more powerful than traditional compilers because you can define your own transformations in that work on the data flow. So in the end, it supports multiple architectures, including RISC-V, and with the library of deep learning kernels, our goal is to select the proper specialization for kernel whenever it's the most suited in the automatic way. So this is nice opportunity for future work. So with all that said, let's look at the conclusions. So we saw the problem that there is not so many libraries focused on training on RISC-V. We looked at the platform, Snitch, and its extensions. Then we looked at the example of layer normalization, how it can be optimized. And finally, at the performance achieved through use of these extensions. So thank you for your attention. So if you're interested in more of research from our group, feel free to proceed to YouTube, Twitter, GitHub, or scan this QR code, and you will see all the links in one place. Thank you.
Thank you. It's almost coffee time, but we have time for a question, if there is any. Well,
Thank you. I was wondering how interrupts are handled when FREP is executing.
Yeah, so normally, okay, I'm not hardware guy, so I can't tell you what hardware is actually doing in this case. For this, better to refer to Akami and Snitch papers. What can I say? That when you have these computational kernels, you're not supposed to have interrupts there. So this is completely out of the question.
Okay. Thank you again. And well, there's a poster there, so if you have more questions, he's in that room. So thank you so much, Andrei. So see you all in the coffee.